Hey guys, this is our amazing project. I'm Kenzie. I'll be explaining the turning system, and then this is my teammate.
Eli, I'll be explaining how the hull works and how to drive it.
I'm Jared. I'm going to be explaining how the skirt works and how it stays inflated. I'm Zavine. I'll be explaining the calculations.
Hi, I'm Eli, and this is the hull of our hovercraft. We have two support beams running across to prevent it from flexing. We also have two more underneath that run perpendicular to make a square. And then we have the steering column with our beautiful Mercedes logo on it. And these two backup steering systems so that if our main one fails, then we can still control our hovercraft. We have the seat so that we can sit on it while we steer. And that's about it.
Hey guys, I'll be explaining our turning system. We developed an incredibly well-designed steering wheel, which allows us to be able to drive our hovercraft with our eyes 100% on the road. We used an intricate wire turning system to pull a back Lazy Susan around so that you're able to be able to rotate. Here's what it looks like when it's turning. As you can see, it turns.
I'm Fardeen, and I'm going to be talking about the center of the hovercraft, which is the hull of the hovercraft. This is the chair. In the center, because of the center of gravity, it is attached to this boot, and this it is screwed onto this boot, and this boot is screwed onto the center. And this thing is what inflates the air into the skirt.
Okay, so I'm going to explain how we folded the skirt and how it works. So first we started with folding all four sides. I'm going to fold just two sides to show you. Fold all four sides, then we put this down like this. Then we fold this like that, so no air can get through. So all four sides should look something like this. And then once we have all four sides and we know that no air gets through, we poke holes all around the bottom. This would be a circle, so you can hover. So how that works is like the leaf blower blows air through the top, and the air goes through the holes, so we have less friction when we are moving.
Hello guys, I'm going to be talking about how we got our acceleration. Our acceleration was 0.09 meters per second squared. We did this by measuring the time it took for the hovercraft to reach to the halfway mark. We then divided it using the equation that's going to show up here. Then we calculated our top speed, which was 2.1 meters per second. We did this by calculating the time it took from the halfway mark to the finish line.
Go.
Guys, I'm going to be talking about how we got our center of gravity. This is important so that it helps our hovercraft be leveled and doesn't look like a seesaw. I did this by using the equation that's going to show up on the screen right now. The center of gravity is 3.5 inches behind the hull. Thank you. Next guys, I'm going to be talking about the CFM. I got the CFM by looking at the lead blowers. The lead blowers told me that it's 473 feet per minute. Yeah.
Okay, now I'm going to be talking about force of gravity. Force of gravity is equal to 804.42 newtons for us. This is done by taking the weight of our hovercraft and driver multiplied by 9.81, which is the measurement of gravity on Earth in meters per second. Force of normal is also equal to force of gravity. Okay, now we're going to talk about force of motion. Force of motion is equal to 7.38 newtons. Hopefully the calculation will be up on the screen right now. Next I'm going to be talking about force of friction. Force of friction is equal to 92.62 newtons. Hopefully the calculation will also be on the screen right now. Coefficient U is roughly around 0.1. Hopefully the
calculation will also be on the screen right now. Thank you.
Hey guys, welcome back to What Went Wrong. So pretty much everything went wrong. Our turning system failed, which was truly unfortunate with the wire snap due to multiple user errors, as well as our backup turning system. As you can see here, it got completely destroyed because we as a collective decided that one singular nail was enough to hold 2 leaf blowers. Unfortunately, we were wrong. What I'd like to change, I definitely spent a lot more time focusing on the wiring of the main turning system, because if I had enough, if I focused more on that, I could have had better tension and better slack, so it wouldn't have failed as easily. Then I'd also design a better backup system. The backup system was designed on a whim. We should have focused more on having a backup just in case because of how dodgy our system was.